Hello everyone, welcome to this lecture. In the previous module, we talked about the definition and classification of ceramics and also discussed about the material science at the nanoscale and several nanomaterials, including zero-dimensional nanoparticles, one-dimensional nanowires, two-dimensional thin films, and three-dimensional nanocomposite, because the nanostructuring is one of the most important approaches to develop novel inorganic materials with enhanced physical and chemical properties. In this module, we are going to talk about defects in crystals, since the physical properties of materials can also be enhanced by defect engineering. Let's start from the zero-dimensional point defect. As you know, a perfect crystal is an idealization, so the intrinsic property can be determined by the compositions, crystal structures, and electronic structure, but no such thing in nature. Atom arrangement in real material should have imperfect crystal pattern. So this indicates that the functional properties of inorganic materials can be enhanced by defect structure engineering. The defect in crystal can be classified into several categories according to their dimensions. One-dimensional defects are point defect, such as a solute or impurity atom which alters the crystal pattern. One-dimensional defects are dislocations. They are lines along which the crystal pattern is broken. Two-dimensional defects are surfaces and boundaries. So they include the external surface and grain and phase boundaries, and they distinguish crystallites. And three-dimensional defects are precipitate, void, and inclusions. They change the crystal pattern over a finite volume. And the material properties is strongly correlated with the defect structures. For example, stronger material, the more powerful magnets, and glassware of striking colors can be realized by defect engineering technology. The point defect, which disturbs the crystal pattern at an isolated site, and we can find two different types of point defect. The first is intrinsic point defect, which can be formed when an atom is missing from a position. So in this scheme, you can find two different types of intrinsic point defect. The vacancy, which governs the migration of atoms on the crystal lattice, and interstice with high energy. Basically, intrinsic point defect can be classified into two categories. One is Frankel defect. A cation is out of place, as shown here. And second is Schottky defect, a paired set of cation and anion vacancies, as shown in this slide. The second type of point defects are intrinsic point defects. So it includes the foreign atoms such as solutes and impurity. These like intrinsic point defects are intentionally added to the material in order to engineer the physical properties of materials. If they occupy a lattice site, it is a substitutional solute. If they fill an interstice site, it is an interstitial solid. And the type of solutes can be determined by their size. This like extrinsic point defect can also be found in ionic solids, so due to the difference in balance between substitutional defect and lattice ion. So one well-known example is oxygen vacancy. So if we adopt yttrium at zirconium site, as you know, the charge state of yttrium is always 3+, and the charge state of zirconium is always 4+. So yttrium, which is substituted at zirconium site, has -1 charge. And in order to make a charge neutrality, 1/2 oxygen vacancy with 2+ charge should be formed. Let's think about again the oxygen vacancy formation in perovskite structure lanthanum gallium oxide. The left side figure shows the lattice structure of lanthanum gallium oxide. You can find 8 lanthanum atoms at the corner of unit cell, and 1 gallium ion is located at the center of unit cell. And also you can find 6 oxygen ion at each face. So if we drop the barium at lanthanum site, you know barium has always a 2+ charge and the lanthanum has always a 3+ charge. So barium, the substituted at lanthanum site, has -1 charge. And in order to make charge neutrality, 1/2 oxygen vacancy with 2+ charge should be formed. This extrinsic point defect can be used to control electrical properties of semiconducting crystals. They can control the type and concentration of charge carriers. For example, boron, the electron deficient solute in silicon, makes holes. And phosphorus, electron excess solute in silicon, makes electrons. This extrinsic point defect can also be used to structural materials. By addition of solute atoms, we can increase the mechanical strength of material due to solution hardening. And the size difference between solute atom and lattice atom induces the lattice distortion, and it impedes the motion of dislocation. And finally, hardens the crystal due to plastic deformation. Distortion by substitutional solute is relatively small, but large enough for hardening of materials. Distortion by interstitial solute is relatively large, so this interstitial solute can be used for high-strength structural steels such as alloys of iron and carbon. Extrinsic point defect also can be found in random solid solutions. At low concentrations, the solutes are randomly distributed. This is the random solid solution. And most of the properties of random solid solutions is proportional to the solute concentration based on this Begard rules, which is related with the lattice parameters of solid solution, given by A minus A0 over A0 equal Kx. In this equation, A0 is the lattice parameter of the crystal in pure form, X is the atom fraction of solute, and K is a constant value. Let's think about the decomposition and ordering of solid solution. At higher concentration, they tend to become cluster. So decomposition means solubility limit. So we can find the solution spontaneously decomposed into a mixture. One exceptional case is solid solution over full range of relative concentration. In this lecture, we talked about the zero-dimensional point defect structures. And in the next, we will talk about the several physical property change which can be induced by the formation of zero-dimensional point defect. Thank you.